my name is Irene. I am a PhD student in Andrea Morelo's group, and I'm here to present an update on the flip-flop qubit. So, two key points that I want you to take from this presentation. The first one is that we show that we can coherently derive the anti-parallel states of the electron and nuclear spin of an implanted phosphorus atom in silicon. And second, that we provide evidence that the driving mechanism is actually the modulation of the hyperfine interaction. So just as a little bit of background, you might already know that implanted phosphorus atoms in silicon are very appealing for quantum computing, as they have demonstrated to have very long coherence times, really high gate fidelities, and being CMOS compatible. There's a big proposal by Kane where the two phosphorus atoms, two qubit logic gates can be performed by turning on and off the J interaction of the two electrons of the phosphorus, but this requires a very precise placement of the donors, so it's not very suitable for CMOS fabrication processes. So in my group, we envision another way of doing a quantum processor, which is the electric dipole mediated quantum processor. Now our 1 qubit gates are defined in the flip-flop subspace. These are the electric dipole transition. And 2 qubit logic gates can be performed because as we pull away the electron from the donor by applying a positive voltage, we create a dipole, an electric dipole that can reach very long distances, and therefore it can couple two distant donors. Good, so this is an optical image of our device. I just wanted to highlight that now we don't just have a magnetic antenna to perform ESR and NMR, but we also have an electric antenna which will drive our electric dipole transition. If we take a closer look, here's an SEM picture of our device. We can see here the magnetic antenna. We have our electric antenna coming here, which we call the donor gate. And we have a bunch of other gates that will help us controlling the electrostatics of our system, and a single electron transistor that we use to single shot read out the state of our system. So in this little region over here, we implant a bunch of donors, and if we took a look at the cross section of our device, this is what we would expect to find, which is a donor underneath an electrode. For this system, this is the Hamiltonian that we have. We have here the Zeeman term, and this term over here is the hyperfine term, which essentially measures this A term measures the strength of the overlapping between the electron and the nuclear wave function. So by modulating, we can electrically modulate this interaction by applying a tone to the what we call the A gate, and therefore modulating the overlapping between the electron and the nucleus, and this will drive this electric dipole transition over here. So the first thing that we can do is we can take a look at the ESR lines of our system. We find, using the magnetic antenna, we find 2 ESR lines corresponding to the flipping of the electron from up to down for the 2 different nuclear configurations. And if we want to find the flipping of the electron due to the electric dipole transition, we have to use our electric antenna. So I'm going to show you now how we find the resonance frequency for the electric dipole transition. So in our devices, we have an electron reservoir that we use to load electrons onto our phosphorus atom. So what we do is when we load an electron, since the electron has 2 lower ground states depending on the direction of the nucleus, we need to apply a pre-pulse just in case we load an electron in these states so that we can enter the flip-flop subspace, and once we're there, we can perform our a voltage pulse or an EDSR pulse, and if it's in resonance, then it will flip-flop our state. Once we've done that, we can perform a nuclear readout, which is just following the normal energy selective tunneling into a reservoir by reading out the ESR1 line. And so we allow for tunneling of the electron we will see a tunneling event if the electron is in the up state, and we will see a tunneling event if it's in the down state. So we're hoping that when we are, and we can perform this measurement many, many times because it's a non-demolition measurement. And so when we're in resonance, what we expect to have is a high probability of nuclear spin flip. So performing this pulse sequence, we finally found our resonance frequency, which corresponds to what we expect from the analytical expression for the EDSR frequency, is with the values for the hyperfine, with a value of a hyperfine of 114 megahertz and a value of a magnetic field of 1 Tesla. So now that we have the electric dipole transition resonance frequency, the most intuitive thing to do is to try to drive it coherently. So that's what we do, and we find that we can do it, we can actually do it, and not only that, but we can drive it with a gravity frequency up to 117 kilohertz, which means that we can drive the nuclear 5 times faster than by using just direct NMR. We can also take a look at how the gravity frequency changes as we change the amplitude of the electric drive, and we find the linear trend that we're expecting. So since we have our resonance frequency, we can also perform some other pulse sequences like a Han echo and study the coherence of our systems. For example, using the Han echo sequence, and we find T2 of 143 microseconds. And we also can do a Ramsey experiment and find that our T2 start is 4.7 microseconds. So we can also look at the coherent oscillations, the Rabi oscillations, by measuring the state of the electron after we perform our pulse sequence. So remember before we were measuring, we were performing nuclear readout, but now we can only look at the spin-up proportion of the electron after we do the whole pulse sequence. So for that, we really need to make sure that we start in the ground state of the flip-flop qubit. So we perform 2 pre-pulses, an ESR pulse and an NMR pulse. So if the state is if we load an electron in this state, the ESR pulse will bring it up, and the NMR pulse won't do anything to it, and then we will read out and reinitialize our state in the ground state. And when we load our electron is in this other ground state, then the ESR pulse won't do anything, but the NMR pulse will flip the nucleus, and we will initialize our state with high fidelity in the flip-flop ground state. So by doing this, then we just perform the EDSR pulse at the resonance frequency, and we also see the oscillations that correspond to the flip-flop qubit. Good, so now we want to study how much the hyperfine changes when we apply different electric fields to our donor. So one way of doing it is just looking at the hyperfine start shift. In particular, we look at the NMR1 resonance frequency, because here you have an analytical expression of what the NMR1 is. You can see that it has 2 terms, one corresponding to the hyperfine and another to the geomagnetic ratio. We assume that for the nucleus, your geomagnetic ratio is not going to change that much as we change the electric fields, because the nuclear is very highly confined. And so mainly the effect of different electric fields. So different electric fields are going to have a bigger effect on the hyperfine constant. So by performing NMR and looking at the NMR resonance frequency with different load voltages, so when we load an electron, we apply either higher or lower electric fields, we see that the resonant peaks shift by an amount of 512 kilohertz per volt. So now we wanted to further investigate this. This means like going higher in load amplitudes, but as you can see here, our charge stability diagram is super messy. So that means that when we're trying to do our pulses and we're trying to plunge deeper and deeper, we might be crossing some other transitions, which means that our system can get to tune or decohere, and therefore we are not able to take any measurements. Nevertheless, with this data that we record, we can also relate the DC start shift to the AC driving amplitude by just following a very naive approach. So we have that you can define the EDSR Rabi frequency to be a term that depends on the change of the hyperfine upon appliance of a voltage, and that is also proportional to the amplitude of that driving voltage that you're using. And also this term here, the 1/2 term, comes from the rotating wave approximation. And so when we take this naive approach, we see that our data points, which are the yellow points here, really match with what we expect with theoretical or with the rotating wave approximation. So as a summary, I've shown you how we can coherently drive the flip-flop transition of an implanted phosphorus atom. I will show that the hyperfine modulation is identified as a driving mechanism. The Rabi frequency is in good agreement with the rotating wave approximation. And also 2 points that I wanted to highlight. We think that the flip-flop encoding offers an electrical drive mechanism for top-up and also bottom-up devices. And it is a prospect of all electrical control for high-spin donors. Thank you so much for watching my talk, and goodbye.